A 1 Week ATAL, Faculty Development Program, FDP, Numerical Approach in Design Thinking. Session 1, Day 1, Name of the Expert, Dr. PVS Ganesh Kumar. Topic: Acoustic Design Spiral and Role of Advanced Numerical Methods. Organized by Department of Mechanical Engineering, Government Polytechnic, Visakhapatnam, Andhra Pradesh, India.
That is where numerical approach comes in. Right? Everything I'm telling about the application, but finally, before reaching the application or quite a treatment, I need to understand how much actually the source is generating the noise. So for that, I use signature prediction methods at the design stage itself. That is where the finite element method or boundary element method, or I'm talking of new method called statistical analysis method. All these three methods come in very handy, where each method has its own advantages and disadvantages, of course, that we can have a separate discussion. But they together form a comprehensive tools to cover the entire frequency range of interest of noise. Therefore, I use not only FEB, I also use C, because FEB has limitations at certain higher frequencies. FE cannot be used everywhere. Though FE is very popular, finite element analysis is popular, it is not very good for high frequencies. It is good for static analysis. It is good for normal low frequencies, etc. But when you're talking about very high frequencies, FE will not be very suitable, because the computational power requirement is too huge in case of FE. Because you have to discretize. You know, most of you may be aware of what is finite element method, where you discretize the entire structure into small elements and then try to iterate in such a way that finally you will estimate the strength of the material in the structure, or the dynamic stresses in the structure. So, or even the natural frequencies, etc. We have model analysis in the FEA. We have frequency response analysis. We can do all those. But then the response analysis is only applicable to certain frequencies because of the limitations in the finite element method. So that is why we need better, higher methods like statistical analysis method. Okay, so that is one thing. So I already mentioned about two-stage mounting system. This is one two-stage mounting system, where I have shown the same diagram earlier. Only thing here is more clear that these are the two stages of mounts. One stage on top, the second stage of the mount is on the bottom. In between there is a structure. We call it as raft, intermediate structure. So if you place like that and carefully work out, then you can come out with a much better isolation, vibration isolation, compared to a single mount working in industry. So this is one application where we have developed two-stage mounting systems for various shipboard applications. And this is of course a limiter, because whenever you are increasing the height of the base, there is always a tendency of equipment to rock. Because whenever you have height, the CG will be difficult to maintain, right? So therefore it tries to rock. To avoid that, we have a design called limiter design, so that it limits the movement to the sideways movement. So the engine will not topple. So that also we have placed here, right? So this is one application. Another is, of course, I already shown this. This is a mastic application. This is a constrained layer damping, where you can start with a rubber treatment and on top of it again a metal. It has a different advantage. Damping has a different advantage compared to isolation. Isolation has a very wide frequency range application, but damping can be tuned to specific frequencies also, a shorter frequency range. Suppose vibration is very dominant, noise is very dominant in a particular frequency range, then this kind of damping treatment is very useful. So where you can suppress vibration noise in a particular frequency range. And in constrained layer damping, another advantage, rubber works in a shear. You know what is shear, right? Shear and tension. In case of this, it actually works in the tension compression mode. Whereas here it applies, shear mode is applied because it's constrained between the two layers. Now, when you are talking of shear mode, the rubber is more effective in shear. So that is why CLD is very effective treatment, particularly reducing the particular frequency range. Then of course this is the enclosure put on a ship compartment, in a compartment where we have enclosed a diesel alternator. And this has a sliding panels because for maintenance of staff to enter and do the maintenance of engine, they have to have some kind of access. Therefore, if you are fully covering it without any openings, it will be difficult for them. So that's why we designed a sliding panel type of enclosure. So in this sliding panel again, each panel will have three layers. One layer is solid wall, you can see outside. This is a solid panel. But inside there will be again wool. Again, that is taken care of retention by one wall called perforated wall. Why perforation? Because the sound has to impinge and get absorbed by wool first. So there is a perforated wall inside. These perforated sheets are made and attached to the inside. So this is how it is normally built, and same thing applies to silencers also. I already explained about the silencers. Then of course composite products I already mentioned. This is FRP foundation. This is the blower, and these are the pipes. This is one pipe. This is a composite shaft for a particular equipment. So these are some examples only. I am not saying FRP is limited to this. These are FRP applications, fiber reinforced applications, so that you can bring down the weight in the equipment, at the same time reduce the vibration and noise. And this is a nice prediction using what is known as FEA, BEA and CA combination, SCA combination. This is of course for a submarine we have done, so it's only a model I'm showing. Similarly for ship I have done, so that the pattern will be like this. Why it is important is the pattern around the complete object, the noise pattern can be predicted. So using that prediction, you can understand where the maximum noise source is coming out. So if you are able to identify where is the maximum noise, then you can attack that particular problem for reduction. So that is the advantage of prediction at the design stage. Because once you are able to identify the design stage itself, what is the problem, where the maximum noise is generated, then your quieting technology also you can apply accordingly. And this is a tuned damper application, where again some kind of iteration has to be done through a numerical approach. And then you design these tuned mass dampers to reduce the vibration from the pump. And you can see without tuned mass damper, this much peak is there, vibration. But after application, it has come down to so low. That means a particular tone, particular frequency is very dominant in a pump or something. Then the vibration will be very high at that particular frequency. If you want to bring down that particular component, then you apply this kind of a tuned mass damper at all four corners. Then you reduce the noise. And the latest one is the active control, as I mentioned. This is application of active control. This is a magneto-rheological damper mounts, we call it, MR mounts. So magneto-rheology is basically what rheology is basically study of viscosity. Magneto-rheology means you are applying magnetic particles in a liquid to get the viscous changes in the liquid, so that it basically changes the pattern of vibration. So yeah, this is what we are talking about. In fact, in this, the equipment involved is very elaborate, not like passive treatment so far we have discussed. In passive treatment, you can see it's a simple application of a rubber mount or a rubber layer, etc. It's very simple passive method, relatively. But here, when you want to really implement active method, you need a complete set of controller along with sensor, along with feedback circuit. Then only the difficulty is in the realization of the controller to suit the required frequencies. This is very effective at the low frequencies. Same, this is whereas the previous one, what I showed, this magnetodielectric mount is basically semi-active. It's not fully active actually. That is why you can see some kind of rubber also here, like rubber mounts. It is a combination of rubber mounts and active control. That's why we call it as semi-active control. Whereas here it is a fully active control. That means you are actually using actuators to control the noise, real restrictive interference. Whereas engine is producing noise, to control it you are putting actuators all around and creating anti-noise. Then it's called restrictive interference approach. Like you can see, principle of superposition or restrictive interference. This kind of realization is very, very tough because you need a lot of equipment. You can see a lot of actuators like this to reduce the noise from a small, even a small source. When you're talking of bigger sources, it will be much more difficult. So that is why it is becoming a very complex domain and a big research area for active control. Because of paucity of time, I'm not going into detail into every aspect. In fact, each is a subject by itself. Of course, acoustic testing is one area which is very important because ultimately, even though you realize some product, whether it is really working as per your design or not, you can test it in such facilities. Here in NSTL, we have this facility called anechoic chamber. Anechoic chamber means I talked about echo coming from these walls, right? The walls echo can be reduced by putting what is known as this kind of sound absorbing treatment. These are called sound absorbing wedges made of different materials, like you can use a wool also in case possible. So this is complete, not only walls, even the top, you can see ceiling also is attached like that. This is called semi-anechoic chamber, whereas if you treat floor also with that, it's called fully anechoic chamber. So there are six total walls as per this room. Four walls here, ceiling and the bottom floor. So all the 6 if you are treating, then it's called fully anechoic. Otherwise, it is semi-anechoic. So in this case, why it is created is to know exactly how much sound this particular equipment is producing. Otherwise, what happens if you are testing the same equipment here? What will happen is the reflection also will add to the sound that you are measuring. Whereas if it is completely absorbing, the only sound produced by your equipment only will be measured. That is the absolute measurement. That's why this is as per the ISO 3744 we call it. As per that standard, we get the measurements in a big facility like this. These facilities are very unique. NSTL has one. Similarly, there are NPL in Delhi and Chennai and Kochi. They have this facility, and Pune also. Arai, automotive station also they have. So very few facilities, 5 or 6 facilities are there in India. So they can be utilized for research area also to do research on sound and noise, etc. In fact, if you measure in the sound like this, it will create a map of sound from where you can identify where is the actual source of noise. In this case, for example, in this vertical pump, the major noise is coming from here. So then you can map onto that particular component and attack that component design to reduce the noise. This is the advantage of having such facilities. This is vibration testing, what we do in our lab. For example, this is an underwater weapon getting tested, whether it is withstanding certain vibration levels or not. Because on board, whenever they are using in ship and all, they have certain vibrations. Ship also experiences a lot of vibration. Whether that vibration is still acceptable for this weapon or not. Because this weapon has to sustain and then operate. That vibration should still withstand. Then only it can operate. So that is simulated here by a vibration table and tested. In fact, this is a mount testing. where we are able to understand how the mount is performing, isolation point of view. So like this, there are many possibilities. Model testing is another approach. Onboard itself directly on the actual object in the industry. Directly you can go with the impact and hit it and observe the natural frequencies. These are all some testing procedures. And ultimately, of course, nowadays we are talking of advanced techniques like acoustic holography, which is different from the earlier talking of, and when I talked of measurement in the acoustic test center, we are measuring with sound intensity or sound pressure. But that is only 2D measurement. When you are talking holography, it gives a complete 3D picture of sound. So that is the advantage of, in fact, that is what you can see here. You can see this is a 3D map of sound around a complete ship or submarine. Like that you can do for a complete equipment also here, a motor-driven pump, for example. You can do. So by that, what you can understand is where is the actual source coming. It is much easier. Because 3D map, you are able to understand exactly, you can point out the exact source. So this is called near field holography, acoustic holography, which has become very popular because of the effectiveness of its method. So having done all this, I have, how much time we have? Half an hour there? 1 hour? Okay. Right, then we can continue. Here we have what is known as, in fact, I've talked about different approaches, but now when you're talking of design approach, you know, and I want to little bit elaborate on one particular aspect at least, because everything we can't talk of design in this 1 hour lecture. I took vibration isolation as one example, where you can talk of how to design the mounting system for an equipment, how the thinking goes into that. So here, what is vibration isolation? Vibration isolation basically, in this case, this is all known. Vibration can cause a lot of failures, physical failures, functional failures, and there are two possible approaches. One is vibration design itself, if you are able to do vibration isolation. Otherwise, the path treatment, I already mentioned about it. Vibration isolation is basically a path treatment approach. Why it is required? Because you need to protect the equipment from vibrations. Also, to reduce vibrations that are coming from the engines. Either way, it has to be done. So that is why vibration isolation is required. And then, what is it? What do you do in vibration isolation? You can see, using of this word is very important, resilient elements. The rubber is a resilient element. Resilience means what? Which stores energy and releases it gradually. Right? Rubber is one such element. You have other elements also like cork and all. Right? But rubber is more popular because it is very effective in the industry. So this is resilient element for reducing the vibratory forces that are transmitted from one structure to another. That means from the foundation to the all around surroundings. So these are vibration, they are called vibration mounts. And the basic theory behind it comes from this particular theory called force vibration. There are two types of vibration. One is free vibration, another is force vibration. Free vibration is something which happens when you just hit one object and you leave it. It automatically oscillates on its own. It's called free vibration. But force vibration means it's a continuously, the force is existent. For example, when the engine is running, it is basically creating a force vibration, because force is continuously on. So in the case of force vibration, in any vibration theory, it is always idealized as a spring mass damper system for mathematical treatment. That is more convenient to treat. Therefore, people use this model. The K represents the stiffness of the spring, and C represents the damping coefficient, and M represents the mass of the equipment, and force is what is being imposed on the equipment. Like for example, because of imbalance, some force may be there. Because of alignment issue, there may be some additional force that is coming in. So forces are present, and they are treated as a sinusoidal forces because it is a rotational object. So that is why basic theory states the first equation that comes out of this in a vibration theory is this only: mx double dot plus cx dot plus kx equal to f naught sin omega t. The f naught sin omega t is the exciting force, mass into acceleration, then stiffness into displacement, and the damping coefficient into velocity of the equipment. So that is, so these three combinations together balances the exciting force. And from this, the x is assumed as this form. Finally, you can derive x as a f naught by root over this term. And after all this, why I am showing this is basically, of course, this you can always see in a vibration theory, in any book on vibration. But why I am showing this is, this has relevance to how isolation is designed. Because ultimately you have to design this particular aspect, the stiffness and damping in an isolator. Equipment is given as a mass and it is generating some force. Now ultimately you want to isolate the subject from the surrounding, or the surrounding should be isolated from this equipment. You need to put a mount, like I showed the vibration isolator. That isolator has the stiffness as well as damper. So that is why we need this particular theory. Based on this theory, you can design an isolator by going to the force balance diagram, it's called. The force balance diagram is basically showing what is the force in the spring, what is the force in the damper, what is the force in the mass, and then it is balanced by the excitation force. So it's called force balance diagram. Then you go to actual final vibration isolation. How it is done is by calculating how much force is transmitted from the engine to the foundation. You can see here, if you are having the mass here and force here, it is transmitting some force through this spring as well as through the damper to the surrounding structure, right? Because engine is what is producing the force. So that force transmission is known as, because it's passing through spring, it is kx whole square. You know, spring stiffness into displacement is force. Similarly, damping coefficient multiplied by x dot, that is omega x we call it in case of sinusoidal vibration. C omega x. So this becomes the transmitted force. Now the transmitted force divided by the excitation force is what is the transmissibility. Ultimately what is transmitted is force transmitted. What is exciting is force, that is exciting F naught. The transmissibility is the ratio of them. Why this transmissibility is important? Because this transmissibility gives you how much actually the isolation is occurring. 1 minus T is basically isolation. Whatever is not transmitted is isolation. Transmission is something which is basically transmitted from the engine. So once you calculate transmissibility through this formula, what is important here is you can see the terms in the final equation. So 1 plus 2 whole square by 1 minus r square whole square plus 2 whole square. Here there are only two terms everywhere repeating. One is xi, another is r in the entire equation. One is xi, another is r. R is basically the ratio of frequencies, the forcing frequency by natural frequency, whereas xi is the damping factor, which is basically how much damping is inherent in the damper divided by critical damping, what we call it critical damping. So if you know this xi and r, you can calculate transmissibility. So that is why this is a very important formula for isolation. Once you know the transmissibility, you can always tell how much is the percentage of vibration isolation. This is the, if you plot that equation as a transmissibility versus frequency ratio, omega by omega n, then you get these curves for different damping ratios. Because there are two ratios. One is R, another is xi. So you have to vary both. You can't vary both simultaneously. Therefore, you have to create, if you have to create a 2D graph, you have to create D versus frequency ratio with varying xi, different curves will come. All those curves are overlapped or superimposed, then you can see the plots. That means there is an optimal value of frequency ratio beyond which only you will get the isolation, good isolation. Because transmissibility, you can see here, is above 1 in some area. And this area is called amplification zone. Amplification zone because transmissibility is more than 1. That means force transmitted is more than the excitation force. That means it's amplifying actually, instead of isolating. So that means ultimately physically what it means is, if you are putting a rubber below the machine, just take a rubber block and put it. It will not work. It can even amplify also. So that means you need to understand the frequency ratio, that means natural frequency of the item, whatever you are putting, should be meeting a requirement of omega by omega greater than √2. You can see here the basic value where it is crossing into the zone where transmissibility less than 1 is place where here, that is basically at a √2. That means your natural frequency of whatever isolator you are choosing, rubber you are choosing, should meet this criteria of omega by omega greater than √2. Then only you are in the isolation zone. So this is the crux of isolation.